Welcome to the final lecture on object-oriented programming and classes. We're going to wrap up this series of lectures in the object-oriented programming notebook by considering why we might want to use classes in the first place. What do they gain us? And consider programming from an object-oriented perspective. What does that mean? We'll also talk a bit about class inheritance, which is one of the major mechanisms for by which classes become useful, essentially. So, when we introduced functions, part of the way that we justified why we might want to use functions is because it helps us organize our code into conceptual blocks. It helps us build hierarchy into our code so that when we write a program, we don't have to read everything that's happening line by line. It organizes our code into ideas. And complex functions may call simpler functions, which may call built-in functions or operations in Python. So from a high level, our program might look like, register new user, subscribe new user to email list, user, like register user purchase, ship goods, that sort of thing. Those sorts of high-level function calls. And then, for instance, in register new user, there might be a function that accepts the registration form. There might be a call that verifies the user's identity. There might be a call that enters the user's information into the database. And the function for accepting the form might validate that the user's first name and last name, or that the user's name has like a first name and last name, that their email address is valid, and the email validation function might make some kind of network request to check that a test email doesn't bounce back. And so we have these levels of hierarchy in our program where we don't have to maintain a high-level picture as we pick apart these little individual atomic operations in the code. This helps us more easily debug our code and helps the code be more readable when we're collaborating with others or with our future selves as we're developing solutions. Classes are another way of organizing our code. Anytime we want to perform a set of related tasks that all center around some particular object with some properties, we probably want to define a class. So, for example, in the admissions website where you applied and registered for the course, I have written, I designed that site and I wrote a class for managing the various sessions of the course. And in that session, I can do things like check if applications should be open or closed based on the attributes of that session. And I can check when the next application period is. And I can do all these operations that are related to sessions of the class, of the course. Sorry, I'm doubling up on the meaning of the word class now. So I can perform all these tasks related to different sessions of the course. And it helps me to group them all into a session object. That way, anytime I'm working with something session related, I interact with the session object. And I can pass session objects around in my code so that different pages, for instance, that might need to work with the next session instead of the current session, I can have an instance of a session object for the next session and an instance for the current session, and I can pass those to different parts in the code and use the same functions and the same attributes, but they'll return different results because they correspond with different sessions. So this is kind of the perspective of object-oriented programming, in which we regard programs as essentially about creating objects and interactions between those objects. So in object-oriented programming, almost every bit of code we write describes an object, its attributes, or its methods. And in fact, that's what we've done thus far. When we write something like for x in range 5, print x, even something this simple, what's happening is I'm creating objects and I'm calling one of those objects' methods, the repr method of x. And given that print, even functions like print, are objects, almost everything we do in Python is either the creation of objects or the invocation of their attributes and methods. We often are passing objects between functions, which themselves are objects. So these, our program becomes essentially a collection of objects interacting. And this can be a really helpful perspective when we're writing code because it helps us remember things like scope. Now, when I'm thinking about a function that accepts some argument, x, I can think of this function as an object. And part of that object is its argument. I can think of its argument almost like an attribute. And so this argument only has meaning attached to this function, because the argument is kind of like an attribute of the function. And so this perspective helps me organize my thinking about the code. Another reason we might want to work with classes is because classes build on each other. Many complex tasks that we wish to accomplish have simpler analogs, and we're simply elaborating on these simpler analogs with more and more functionality. So one package we'll work with a lot as we move into the data science portion of the course and the scientific computing portion of the course is pandas. Pandas introduces a data frame object, which is a nice table type data structure. And when we create a data frame, one way of creating it is like this. And we can see we give the data frame a dictionary with a name for a column, and then the values in that column. And the data frame object itself is kind of like a dictionary of lists, where the keys are the different column names, and then each column is a list. Now, a data frame has a lot more power on top of that. But way down in kind of the hierarchy of data structures that we're building upon are dictionaries and lists. And on top of those are things like NumPy arrays, which we'll talk about soon. And then from NumPy arrays, Pandas develops this ND frame. And then on top of the ND frame is built the data frame, the thing that we'll be working with quite a lot. And at each step in this hierarchy, we're elaborating on the functionality or tweaking the functionality to give ourselves certain advantages or additional capabilities for handling more complex tasks. So we go from something like a list or a dictionary where we can easily store and retrieve data, but not do a lot with the data structure as a whole, to something like a data frame where we can very quickly transform columns of data into new columns of data, or aggregate those columns into representative statistics, or slice the data frame into groups and aggregate the data by groups. All sorts of things we'll see in future lectures. So, given that kind of chain of inheritance, let's talk about how inheritance works in some detail. So, as I mentioned, often we will be building off of existing ideas in other classes when we're defining new classes. We could, for instance, try to create an implementation of rational that uses float arithmetic and inherits from float. It turns out this is not so easy to do. I've tried it, but it's something we could imagine doing. For the sake of a simple example, we'll write some classes that define very simple shapes. And this will be pretty easy to understand and follow, and it will illustrate how inheritance works. So we'll define a rectangle object, and it will have a height and a length. Rectangles, 4 sides, length and height. The sides meet at right angles. So these are the only attributes I need to define a rectangle. And the rectangle will have 2 methods, area and perimeter. The area, of course, is just the height times the length, and the perimeter is just 2 times the sum of those 2 things, the side lengths. And of course, I could create a rectangle with a side of length 4 and a side of length 2. And I could ask, what is the area? And I would get 8. 4 times 2. Perfect. Now, we know that there's a particular kind of rectangle called a square, where all 4 sides are of equal length. So we could create a subclass of rectangle called square. And square would inherit from rectangle. Rectangle inherited from this object class. Object, we can see, is written in green, meaning it's a built-in object in Python. And it's the class from which all other classes inherit. It is the base class of all classes in Python. It defines how objects will work, any kind of object. And it contains a lot of very fundamental code for the functioning of the Python language. Square, on the other hand, is going to inherit from rectangle, which in turn inherits from object. And for square, we're going to overwrite the init method of rectangle. And instead, we're going to initialize a rectangle with a height and length that are both equal to just the length of one side of the square, because we know that all sides of the square are equal length. We use this super function to essentially retrieve the superclass of square, which is rectangle. So square is a subclass of rectangle. Rectangle is a superclass of square, meaning it sits above square. So this evaluates just to rectangle. This is the same thing. These 2 different ways of writing this initialization. So we're going to initialize a square object by initializing a rectangle object with two sides of the same length. When we do that, we can create a square object by simply passing in a single parameter, a single argument, the length of one side, and then we can call area and perimeter. Notice we never had to define how area and perimeter work for a square. It inherited those functions, those methods, from the rectangle class. We already know how to do them because of the rectangle class. So this is a simple example of inheritance, and when we build up more complex chains of classes, we'll often want them to inherit from one another to propagate shared functionality. And we'll only define in the subclass whatever methods we want to overwrite. And it's not unusual that when we overwrite or override a superclass's method, that we will in fact call that superclass's method as part of the overridden method. So here we overrode the init method, but as part of that overriding, we call the rectangle's init method. Another example is back in this init method for data frame. There's a whole lot of code here that does all sorts of things different from the ND frames init. But at the very end, we call init from ND frame. So we do all this stuff, and then at the end, we still call the parents method. This is a silly example, but for instance, we could add to the area method print calculating area of square. And then we would do super square self dot area. That didn't quite work. I need a return here. There we go. And we get the same thing as we did before. We got the area of 25, but now the squares area function additionally prints out this little message. Rectangle, on the other hand, does no such thing. So, inheritance allows us to skip defining a lot of methods that we might want to use from a parent class, and we can also totally or partially override a parent class's methods in the child class. One thing to be aware of is we sometimes want to check what type of object we're working with. We've done this in the past in two different ways. One is to simply print out the type of object we're working with. So S is a square, so its type is equal to square, this class that we defined earlier. Type of S is not a rectangle. S is not a rectangle. However, S does inherit from a rectangle. Often we're not interested if the object is a particular class, but we're interested in if the object inherits from that class. Meaning, is it reasonable to expect that S, a square, acts like a rectangle? And in that case, we want to use the isInstance function, which will check if S inherits from any of the classes we put here on the right. And since S is a type of rectangle, it is a square, isInstance S rectangle returns true. S is not a rectangle, it's not a rectangle object, but it does inherit from rectangle. One case where we use this a lot in practice, for instance, is we might have well, this is not so common in Python 3, but this was very common in Python 2. There were Unicode strings, which don't exist anymore, not defined, but this existed in Python 2. And there were regular ASCII strings, and those would have been things like str. And it was very common that we would want to check if something was a string. But instead of checking if something was a Unicode string or a regular string, both of them inherited from a class called baseString, which also does not exist in Python 3. But it was very common in the past, in Python 2, that you would check if a string inherited from baseString. And then it could be a Unicode string, it could be an ASCII string, but you would know that it should behave like a string. And so we should be able to work with it like a string, even if it's not exactly a particular type of string. Even if it's not exactly an ASCII string or a Unicode string, we might not care about that. We might just care if it's string-like, in which case we would check if it inherited from baseString. In Python 3, this is no longer the way in which strings are organized, so we don't do this anymore. But that is an example from Python 2 that sort of illustrates a very common use of isInstance. So that concludes our discussion of object-oriented programming. I'm going to leave you with this question to consider. What are some built-in Python objects that might inherit from the same parent class? And in fact, I'm going to pose this question on the message board. I'm curious to know what your thoughts are. Inheritance of built-in classes. Exercise. So share your thoughts. And let me know what you think. I'm going to do one more lecture this week. It's not going to be from a notebook, but we'll be looking at some programming exercises that you can do to sharpen your skills and apply some of the things we've learned using some tools outside of the course tool set.